So today's class, we're going to continue with solving story opportunities. I don't call them word problems, I call them story opportunities, because every time you say word problems, you're setting yourself up to have a problem, right? We're not going to have any problems. We're going to be successful, and we're going to conquer these things. So today, we're expanding a little bit because we're going to go into chapter 5, which is a long way away from chapter 1, but it just gives you another tool, for example, of how you would solve the second problem you were just working on, that stocks and bonds problem. It's just another way to approach it, but now it uses 2 variables instead of 1. In fact, many of you just naturally went to 2 variables when you were solving this. Your book in section 1.3 shows you how to do it with just 1 variable. So we're going to be doing that. Your projects are due today, so throw them in the folder. And then quiz number 1 is on Monday. And what I did is it was originally supposed to be on classes 1 to 5. But since 5 was a snow day, and I know that not all of you watched the video because I could tell by how many views there were, and not all of you filled in the lecture notes. It's probably the one time I will really take care of you and enable that kind of behavior. So I took 5 off of the quiz for Monday and I rewrote it. So it will be classes 1 to 4. If that happens again, I'm going to have to be not so kind and nice and enabling, okay? So remember, for your quiz, you can take one of these little guys in, little index card. I have these on my door. Or if you want to save some trees, this is a 5x3. You could take some recycled paper and just cut out a 5x3 and take your notes in. That's fine with me. So you're allowed to bring this in on Monday. And the other thing I forgot to tell my other class is, if you're one of these students, are you listening, Jonah? Okay. If you're one of these students that needs more time than you usually get from the teacher, one of the great things of having 10 to 10:40 optional is you're not anywhere from 10 to 10:40. I mean, what I mean is you're not in another class. So you can come in early and start your quiz, because I'm going to give you 20, 25 minutes on average to do a quiz. So if you think you might need 30 minutes or 45 minutes, come in early. You know where I live. Where do I live from 10 to 10:30? Studio. So just come and get me, and I'll give you the quiz. And down underneath here are privacy shades. You put this up around your quiz because you're sitting really close together. You put these up, and you can start without me being here to proctor it. Yep, Cooper? I don't know. I'm trying to remember. Oh, you mean if I counted all the parts? I don't know, 15, I'm guessing. It's like, I don't know, just like, I'm trying to remember it. I just printed it out this morning. There's probably 6 different parts, 6 different questions, and some of them have multiple parts. There's some true false, like I've been doing with you, and I've suggested on every single one of your homeworks, I say look at preview exercises, all right? And if you look at the preview exercises, at the end of the chapter, right before that, there's a bunch of true false questions. Really good practice for my assessments. But if you've been doing your homework, which most of you have, I've been peeking at everybody's homework assignments. As I was telling my first class, my math lab is great for those of us who like to do a little, like voyeurism kind of stuff. I can go in and see, oh, Cooper's doing really great. He's done all his homework assignments, or so-and-so hasn't even done one of them yet. Anyway, but that may be your choice. You may be choosing not to have homework count. So it's really up to you, but I like to keep an eye on how you're doing. Okay, so today we're going to start, and we'll have our DJ in the class, Connor, start us off. Class 6. Okay, so you probably have seen what a system looks like of linear equations in 2 variables. If you have 2 variables, you need 2 equations. looked at simultaneously. In fact, when I was taking math, they were called simultaneous equations. Now they're called systems of linear equations. So here's our first system right here. Notice how your book uses this set of braces here so that you group that together. You see this as one system, okay? One way to solve these systems is to graph each line. This is a straight line, and that's a straight line. This line has a positive slope. This line has a negative slope. So if you were to graph them by plotting a bunch of ordered pairs, x and y, for each line, this second equation here, x minus 2y equals 6, is shown right here by this blue line. And this first equation, x plus 2y equals 2 is shown by the blue line. And x minus 2y equals 6 is shown by the red line. And when we ask for a solution to a system, if there is one, visually what that solution looks like is where the two lines intersect. That's a point that they both share, a point that lies on both of these lines. It's called a common solution, or the solution to the system. Okay, so if we wanted to check that point 4,1 is truly a solution, you go back to both equations and you put in, it's actually should be, I have a typo here, it should be 4, -1. So you go back and you put in 4, -1 in both of the original equations. So x is 4 and y is -1. 4 minus 2 equals 2. Yep, so that checks. And then it has to also work in your other equation if it's going to be a common solution. They both work, okay? So when you find a solution to a system, it's not just x equals a number or y equals a number. It's actually an ordered pair, so you have to solve for both your x value and your y value. So anytime you solve a system, you're looking for an ordered pair. That's the solution. This is your common solution. Now, the problem with graphing, this is usually the first type of method that you're taught when you're first learning about systems, solving systems, is you solve through graphing so that you have a visual for the representation of the solution. But it's really kind of hard if you have a solution like this, 17/9 for x and -3/7 for y. You're not going to be able to get those values off of a graph unless you have GeoGebra and you ask it to tell you the value, right? So we usually, when we're solving systems, we usually rely on an algebraic method. And there's two algebraic methods to solve a system. One is called substitution, and the other method is called addition. Some of you may have learned a name for that called elimination. This has a variety of different names, the second method. So the first method, though, as far as I know, or I've ever seen, is always called substitution. And it's exactly what it sounds like. You take a look at your system and you say, can I use one of those equations to write one variable in terms of the other variable? Well, you can do that for both of them. But what you usually try to zero in on is you look for one of the variables. The easiest way to solve one of these equations for one variable is when it has 1 for the coefficient. When one of your variables has a 1 for a coefficient. So if you zoom in here, you see that this second equation says plus y that has 1 for a coefficient. So this is really easy to rewrite as y equals 1 minus 2x. So you rewrite your equation in terms of one of the variables. I could have done it for my top equation as well. I could have solved it for y, but I would have had yucky fractions. So we try to avoid fractions whenever possible, right? Usually. Now you can say, you can literally use the word substitute. I'm going to substitute this value of y back into the y I see in my first equation. So substitute into the first equation. So now I have 3 times x plus 2, and instead of writing y, I write what y equals to right here. 1 minus 2x equals 4. So now the nice thing is I have one equation with one variable, no problem to solve. I just use my distributive property and I get 2 minus 4x equals 4. I get negative 1x plus 2 equals 4. Negative 1x equals 2. X equals negative 2. So half of my story is now known. I know the x coordinate of my ordered pair. But you don't stop there because you've got to find your y value. Okay? So your y value, to find your y value, what's really important is you always go back to one of the original equations. In other words, you don't want to go back to this equation right here, because if you made a mistake when you converted this equation to this one, you won't see that you made a mistake. So if you go back to your original equation and you made a mistake, your original equation is going to show you that the left side doesn't equal the right side. So to find the y value, go back to an original equation and go back to an original equation, pop in the x value, pop in x value, solve for y. It doesn't matter which original equation you go back to. So let me take 3x plus 2y equals 4. I just said x was negative 2, so I'm going to put that in, and I'm going to solve for the y value. Find y value. Go back to an original equation, pop in the x value, solve for y. Okay? So negative 6 plus 2y equals 4. 2y equals 10. Oh, almost sneezed. Y equals 5. But if you're a little extra careful, you're going to say, okay, here's my solution. And to be really extra careful, you take that solution and you plug it into the other equation just to make sure everything's kosher. 2 times negative 2 is negative 4 plus 5. Good, gives me 1. So this would be the point of intersection if you were to graph these two lines. That's the substitution method. Okay. I'm going fairly quickly because I guess I'm making an assumption that if you're in Math 107, somewhere in your algebra background, you've seen this method before. Is that a yes, kind of a shaking of the head? All right. The other method says, and that's why I kind of like both of these names at the same time, because the addition method tells you what you're doing. You're adding the left side and the right side, and the elimination method tells you why you're doing that, because you're literally trying to get rid of one of your variables. So now this is a totally different approach, but it gets you to the same solution. It's just a different idea. So if you look at your system, okay, so now if you look at your system and you don't use substitution, you say, is there any way I can, if I add my left side and I add my right side, that I can eliminate one of my variables? Well, let's try it right now as it's sitting here. 3x plus 2x is 5x. 2y plus 1y is 3y. 4 plus 1 is 5. And you say, oh, crap, that doesn't help me if I add the left side to the right side in this system, because now I still have one equation with two unknowns, so I haven't gained anything. So now you say, okay, so now what do I do? Well, if you go back and you take a look at this again, 3x plus 2y is 4, 2x plus 1y is 1. You notice that if, I'm going to focus on the y's here because it's less work. If this top equation had 2 for a coefficient, what would be the coefficient of this second equation so that when I added these y's together, I got 0? Negative 2, right? And because you're dealing with equations, you have the right to multiply the second equation on both sides by any number you want. But why not pick the number 2, negative 2, to multiply each and every piece of that equation? You haven't changed it, you're just rewriting it. as an equivalent equation. So now rewrite your system all over again. Now your second equation looks like this, which is totally equivalent to your first equation. And now try adding them. So now you add everything on the left side and everything on the right side. When you add everything on the left side, you get negative 1x. This becomes a nice, beautiful 0. You could say plus 0 if you want. And then on the right side, you have 2. And then when you solve for x, you get x equals negative 2. Same as we did before. Okay? And then you would go back to one of your original equations and solve for y. So that's the idea behind addition. Sometimes you're not as lucky to have a variable with a coefficient of 1, and you've got to multiply both equations by a number. The key idea here is to make, oops, I didn't mean to do that, is to make the coefficients so that they're opposite. Okay, so let's suppose we were looking at this again, and let's suppose you didn't want to make this a negative 2, and you were going to try to get rid of the x. So you have lots of choices here. One choice would be to multiply the top equation all the way through by 2, making this a 6x. Then you'd multiply the bottom equation through by negative 3 to make it negative 6x. You could pick any multiple you want, 12, 24, 120. The key is they have to be opposite coefficients to eliminate them. Okay, so those are the two methods when you have a system to solve for the common solution. So we're going to be using this today as we work through some of these story opportunities. So let's take a look at one similar to the one you were working at the end of class 5. This involves an investment problem, just like the first one, except for now we're dealing with a scholarship fund. So Austin, you want to read this one for us?
As little money in high risk as possible. In fact, we solve this problem using one linear equation comparable system. Where text demonstrates how to use comparable to solve this type of story opportunity. Section 1. So let's take a look at how to use it.
Okay, so if you look in section 1.3 of your book, you will see how to do this very problem, same thing, with one variable. Today we're going to look at using 2 so we can use what we just learned with solving a system. And I think for most students, this is the preferred way of doing it. So notice how I've set up this chart. On the left-hand side of my chart, I have sort of the idea of what I'm looking at. I have two types of things. I have a low risk and a high risk investment. When I define a variable, the language I use has to represent a numerical quantity. So if you look at the column, the first column here, notice it says amount invested. That's certainly a number when you say amount. The only thing I don't like about what I did here is I didn't put the unit, so I would put dollar there. Notice the other idea of this problem involves the interest you earn on each investment. Excuse me. And that also should have a dollar after it. So whether you create a table or you write out everything, if you don't have a table, then you want to do something like this. If you write an X there, then, and you're not using a table, you want to say X is the amount of money invested, dollars after that, in the low risk fund. Y is the amount, and this is where you can just use little dittos like this, invested in the high risk fund. So if I look at an equation that involves X and Y, I know what the heck X and Y is, okay? Or you could use this little table like this, and the neat thing about this table is you already have your first what is equal to what. To come up with an equation, you'd have to say what's equal to what. So what's equal to what here? The amount of money I put in the low risk plus the amount of money I put into the high risk equals $10,000. That's my what equals what. There's my first equation. Voila. Right there, the first column. X plus Y is equal to $10,000. Okay. So if I'm going to come up with a system, I need to have a second what is equal to what. So I'm going to come up with a system of linear equations in two variables. Okay. So somewhere in this story opportunity, I have to talk about a different idea involving X and Y. And that different idea is how much money we earn on the investment. That's called the interest income. Okay, so the interest income earned on X dollars is 4%. So when you write this expression only has one unit. This number, 0.04, represents a percentage. It's unitless. It has no units. So the only unit here is whatever the unit is for X, and X is the number of dollars. So this represents a number of dollars. It's the amount of interest income. Amount of interest in dollars earned on X dollars, right? That's the amount of money you've invested, X dollars. I don't know how many dollars it is yet, but if I take 4% of those number of dollars, that's the amount of interest I'm going to earn. Notice if I go up to my chart and I multiply straight across, I get this expression. That expression is equal to the amount of interest in my low risk fund. Just read your headings and your headings and your row names. Similarly, if I multiply 0.08 times y, I get the expression 0.08y, and that equals, I read my total, my top here, my column, amount of interest on what? My high risk investment. Or down here, if I'm not using a table, I write out what 0.08y means, amount of interest dollars earned on y dollars. So now I look around the rest of my story and I say to myself, they either got to tell me a total amount of interest or they have to tell me something about the relationship between these two, like one is $2,000 more than the other or whatever it is. You've got to know either a total or a relationship between these in order to come up with your second what equals what. So you read the rest of your story or you reread it because you've already read it once, and it says that the expected return is $550. So you now know that these two things add up to $550. God bless you. So now you come into here and you erase the second what equals what, and you replace it with 0.04x plus 0.08y equals 550. And there's your relationship between the amount of money you originally invested and your return on each amount. So if you were to solve this system as you look at it right now, what of those algebraic methods would you have preferred to use? Which one do you think you would use if you were going to solve right now? Substitution. When you use substitution, you're going to look at that first equation. You're going to either rewrite that equation in terms of y, like y equals something, or x equals something. That's what your book shows you in section 1.3, is how to write it in terms of one variable. So if you solve this equation for y, it would be y equals, always the first number is your total, take away how much you put in your other investment. And you put it in parentheses because that represents $1 amount. Now you use that and you substitute that amount right in there for y. And now you'll get a beautiful equation, all in terms of x, that you can solve pretty easily. Okay. So now you have that second equation all in terms of x. You could change it so you have no decimals, but since most of you are working with calculators now, the decimals don't bother you. So you just use your distributive property and you get 0.08 times 10,000 is 800. 0.08 times minus x is 0.08x. You combine these two like terms and you get negative 0.04x plus 800 equals 550. And don't get nervous that you have a negative there, because when you subtract 800 from both sides, you're going to have a negative on the other side as well. So you'll end up with a positive value for x. So that gives you negative 0.04x equals negative 270. So x equals, what is it, 6250, something like that? 6250. So in your original fund that was $10,000, you decided to put 6250 in the low risk fund, and the remainder, 10,000 minus x, 10,000 minus 6250, which is 3750, in the higher risk fund. You notice those two things add up to 10,000. And if you really wanted to check your work, you would take 4% of 6250 and 8% of 3750 and see if that equaled 550. But since I'm the teacher, I must have done it right, right? Now, it's just because we did it in the first class, so I know it's okay. So that's how you use solving a system of linear equations to do a problem you could have done at the beginning of the hour with one variable. But as I say, when you have these dual investment kind of story opportunities, it's sort of a natural inclination to give a letter to one of the investments and a different letter to the other. But to solve it, you always go back to using one variable. Right? Any questions on anything here, either the chart or the equations we came up with, anything at all? What would you like me to do? Sure. Okay. Let me give you a little hint. My hint is all algebra textbooks do from this point on with these types of problems is they change the story. The method is exactly the same. Here they might be talking about putting money into different types of funds. Another thing they could do is talk about making a mixture of nuts and different types of nuts and granola, and it costs so much per pound. And so that cost per pound is acting sort of like the investment, the interest percentage. They just change the story, but you come up with two different equations and you solve them using, most of the time, substitution like we just did. So the concept doesn't really change. It's really just the story. And the more you practice these, the more confident you are. And as I walked around, I talked to all of you about writing these 4 sentences out and how critical that is to understanding the problem. And I know I could get up and do a song and dance and I still may not convince you, but if you want to be really good at this, this is really where the hard thinking happens. Because once you get these written out, usually it's not too hard for you to say, oh, now I know what these two things equal. Okay. Can I move on here, Jonah, or do you still need it? Okay. So the last type of problem, and this is different. This year, if you've taken 107 before, I've come into chapter 5 to talk about a break-even analysis. And it's because a lot of students that take this course are in the business programs here, and they're going to be going off to some type of business school. So the idea behind break-even analysis is you're some type of company, you've invested some amount of money into making a product. It could be bicycles, it could be wheelchairs, it could be generators for those of us who lose our power all the time in New England, whatever it is. You invest some amount of money into producing a product, and if your company is successful, you'll actually then sell your product, and hopefully the cost that you've decided to charge for each one of your items will produce what we call a profit. Okay? But in order to get a profit, the money you take in has to be greater than the money it costs you to produce that number of units. So break even is literally the number of units you have to sell where your revenue and cost are equal. No profit, no money in the hole, no money, where I'm on Wall Street now, I'm the wolf and I can throw money around. No, I didn't see that movie, but I've heard about it. So anyway, so with a break-even analysis, you're looking for where your revenue is equal to your cost. Okay, now I made myself a little note here. It says note, use of functional notation. Because this is chapter 5, when we write our equations, we're just going to use the normal C equals, X equals, Y equals, R equals, but your book is going to use functional notation. So I want to show you how we'll write it right now because we haven't covered functions and how you see it in the book. And don't get nervous because it's a little different notation. So let's try, Cooper? No, where I made the typo, and that's where I was going next, is right here. This should be 400. Yeah, because before I even started in my first class, someone said, "You're going to have negative wheelchairs here," and I just ignored it and did it and said, "Yep, there's a typo." And someone pulled out the book, and I said, "It's either 6,000 or 400." And it was 400. Yeah. So thanks for catching that. Okay, so let's read the problem. Canberra, you want to read us the problem we're going to look at today? Okay. What are you asked to find? Number of wheelchairs. As fast as you answered that, with exactly the right language I wanted to hear, number of wheelchairs, that's your first step. That's the definition of your variable. So let X equal the number of wheelchairs. Perfect. Okay. So we want to know how many wheelchairs have to be sold for the company to break even. So we need to come up with a cost, an equation for the cost. If we were in chapter 5, I would be calling it a cost function, but we'll just say an equation for cost and an equation for revenue. Okay. So an equation for cost. Equation that would equal the cost to this company of producing X number of wheelchairs, however many I'm going to produce. What would the equation look like? Yep, Connor? Yep, my starting point, 500,000, my fix, plus 400x, right. You recognize this as y equals mx plus b, except for I've got my b part first. And often when we read something, we usually put the b first, really, when we read it, because that's our starting point. That's our y-intercept. We're going to start up at 500,000. That's our initial investment, our initial fixed cost. And we hope as our line continues to go up as we move to the right, that at some point our cost and revenue will meet, and then we'll produce more and we'll make more money. Good old capitalism at its best. Okay, so that's the fixed cost. How you see this, if you read this in your textbook or you see some of the problems on my math lab, and don't let it get you all like weirded out, you'll see this. Since the cost depends on the wheelchairs, our independent variable depends on the wheelchairs, the actual equation is going to look like this, where you see this C parentheses X. That means C of X. We haven't gotten to functions yet, so when you see that on your homework, just replace it in your mind with C. That's all. Just use the letter that's in front of the big capital letter. Okay, we'll get to this later. It doesn't really change what you're doing to solve the equation or to find the break-even point. So revenue, what's the revenue? How much revenue am I going to bring in? in terms of the number of wheelchairs I sell? Anybody? 200x. Let's see. Each wheelchair will be sold for 600. I think I see what you're doing. You're looking at the difference. You're already starting the difference between costs. So if I'm asking how much money I take in if I sell 10 wheelchairs, what would you tell me, Connor? No, you can't just look at the production, right? Because you haven't dealt with the 500,000. So just how much revenue am I taking in? Yeah, $600. So it's a constant like that. Oh, 600x. Sorry. Okay, didn't hear you. Okay, so there's my revenue equation. For each wheelchair I sell, that's this number. I get 600 apiece. Okay, what would it look like in the textbook or on your My Math Lab homework? It's going to look like this. But again, don't let that get you all wigged out. Just replace that thing with the big capital R. Okay. Now, how do we find the break-even point? We solve this as your system. Here's your system. You say, when does C equal R? When does C equal R? So you set them equal together, equal to each other. Okay. And you solve for X. So you're saying, when is my cost equal to my revenue? You subtract 400x from each side, you get 500,000 equals 200x. You divide both sides by x, and what do you get when you do that? What'd you say? Let's see. Let's see. 500,000. Here's my 500,000 divided by 200. 2,500 wheelchairs. So if my company's lucky enough to sell more than 2,500, I'm golden. What does this look like if I were to graph each one of these? Well, let's take a look. Let's have Y1 equal 500,000. I'm definitely going to have to change my window. I can't use Zoom 6 because I'm going to have more than 10 on my y-axis. I'm going to start at 500,000, right? Plus 400x. And my other equation is 600x. So I got to deal with pretty big values for my axes. So let's see what would be reasonable to set my table. So I'm going to start at, am I going to start at 0? I could start at 0 and increment by, I don't know, 100,000. But I think maybe I'll just start at 500,000. So I'm going to put it at 500,000. Oh, look at that. It won't even take that many. Oh, I wonder what it does. I know. I'm just, all right. And how should we increment? By one wheelchair at a time, 10, 20, 30? I don't know. We don't know. But so we know because we've solved this. So we could say 100. That seems reasonable. And so that's my table. So if I was using the numeric check, I'd want to know when the y1 equaled y2. So I would do my numeric check like this. And what happened here? Something happened. Oh, it's got x equals 500,000. That's not what I want. Thought I said table start. Let's ask. I don't want it to ask. What's going on here? Start. I guess it's just too big that it's putting everything in. Let's go to let's graph it first. Let's do that, and then I'll come back to this. I don't want to waste your time. All right, so let's start it at, this is what I thought I was doing, was setting the window, and I was actually on the table. Let's start it at 500,000. Let's go up to, I don't know, if I put 2,500 in there, I don't know how big I am, but let's go up to like 1.5 million or something. I hope that's big enough to see it all. Let's have, oh, this is my X scale. I'm sorry, folks. This is what happens when I try to hurry. We know our answer is 2,500, so I'm going to start out at like 1,000. And I'm going to go up to 3,000. And if you didn't know the answer ahead of time, you would just play around with your window until you could see both lines being graphed like we did the other day. All right, now let's see what kind of graph we get. Quit. I have an error, of course. My range. What's wrong with my window range? 1 to 3. My X min is much more than my X max. Oh, what was I supposed? I wanted to put. Yeah, I wanted to put 1.5. Thank you. One more zero. And what I wanted, where did I want to put the 100 on my Y scale? Okay. So let's take a look at the graph. Ooh, I just got there, right? So if I really, you can see this. So if I change my window just a little bit and have my X max or my Y max go out maybe to 2 million. 1, 2, 3, 4, 5, 6. Now I should be able to get a nice intersection point. So there we go. Yeah, that's much nicer. Now, do you remember how you get the intersection point? Do you remember where you go? Second trace, which is your calc button. Yep, second trace. You say enter. I want to intersect. And this is the cool part. Enter, enter, enter. Boom, boom, boom. And there's your answer. For 2,500 wheelchairs, this is how much money I'm going to make. Okay? So that's how you could use your calculator to find the answer. Sorry, I kind of screwed that up a little bit in terms of thinking I was doing the window when I was doing the table, vice versa. Let's capture that. Done that 3 times now. I don't want the whole thing. See, I'm looking at the clock and I want you guys to have time to work. I'll put the picture in. Why don't you get going with your worksheet and work together, use your flags if you need some help, and I'll get that picture in there. Any requests for music? What do you want, William? Didn't you used to have a favorite? I thought before you had a favorite. Oh, you did. You don't? Okay.